Hello, this is Syke, and welcome back to my channel. Today I'm going to talk about the relationship between error in classical test theory and having a clean brain. Now, we typically think of errors as some kind of mistake. However, in classical test theory, error is not exactly a mistake, but instead, this is going to reflect some, let's say, inherent aspect of the measurement process itself. So, error can be random or systematic, and reliability is concerned about random error, whereas we can think about the validation process as being partly concerned with, let's say, the identification and removal of systematic errors. So, to better understand error in classical test theory, I'm going to turn to an infamous case of Mr. Brown. I've actually pulled this example from a book by Lord and Novick. This has become kind of a Bible, if you will, of classical test theory. It was published in 1959, so it's interesting to see the language that's used to describe Mr. Brown. But nevertheless, we can still take important lessons from this example to learn about the concept of measurement error. So let's take a look at this quote. Suppose we ask an individual, Mr. Brown, repeatedly whether he is in favor of the United Nations. Suppose further that after each question we wash his brains and ask him the same question again. Because Mr. Brown is not certain as to how he feels about the United Nations, he's sometimes going to give a favorable and sometimes an unfavorable answer. Having gone through this procedure many times, we then compute the proportion of times that Mr. Brown was in favor of the United Nations. So let's say that we repeat this process with Mr. Brown an infinite number of times. So basically, we ask him about his opinion of the um, United Nations. Sometimes it's favorable, sometimes it's unfavorable, and so forth. If we were to plot these scores, what would the scores look like? And you can see that we're going to run into the same situation if you watch my video about truth and classical test theory, that Mr. Brown is quite similar to um, the issues that we were facing with the door and trying to determine an exact height. Mr. Brown's scores, if we were to plot these scores, will follow a normal distribution. So let's just take a look, and let's say with observation 1, Mr. Brown's score falls over here, slightly to the left, so it's, let's say, a little unfavorable of the UN. Mr. Brown's score, let's say with observation 2, is somewhere over here, somewhat more favorable towards the UN. And like I said, this kind of theoretical distribution of scores would constitute his attitude. Sometimes when we make an observation, it's going to fall to the left, sometimes to the right. Most of the time, it's going to fall around what we would call the true score, which would be the average or the expected value of this distribution. When we think about error, error is just going to be the difference between the score that I observe and his theoretical true score. So for example, with observation 1, the difference between his score here and this true score would constitute error. Same thing with observation 2, the difference between his observed score and this theoretical true score would constitute error 2. With respect to populations, we can derive what's called a standard error of measurement from the formula that I provided to you before about reliability in a different video. The standard error of measurement tells us, on average, how much can I expect my observed scores to fluctuate around the true score. So in other words, it tells me in a sense how much my observed scores are going to bounce around the true score. So let's take a look at how that is calculated. Here I've got the standard error of measurement is equal to the standard deviation of my observed scores multiplied by the square root of 1 minus reliability. So anytime that you want to understand an equation, I have found that it's very helpful, at least for me, to think in terms of extreme cases or extreme situations, and then see what happens with the results that I get. So let's look at a couple of extreme cases with respect to reliability. So here I have the same equation. The standard error of measurement is equal to the standard deviation of my observed scores multiplied by the square root of 1 minus reliability. So if I want to think of an extreme case, let's pretend that reliability is 0. Well, what's going to happen to my standard error of measurement? Well, I have 1 minus 0, so this would just become 1. And this would reduce basically down to 1 times the standard deviation of x, which would just be the standard deviation of my test. In other words, when reliability is 0, all of my variance is going to be error variance. So when reliability is 0, my standard error of measurement will equal the standard deviation of my test. That would constitute, or that would be my maximum value. So let's go back to the original equation. Let's think about what would happen in a second extreme situation. Let's pretend that we have perfect reliability. So in this case, reliability would be 1. Well, now what's going to happen to my standard error? Well, all of this here would drop off to 0. And then my standard deviation is also going to drop off. So we're just left with 0. When reliability is perfect, my SEM will equal 0. So the standard error of measurement, like I said, is going to be used in order to get a sense of, let's say, on average, how much are my scores going to fluctuate around the true score. That value is going to range from 0 when I have perfect reliability, and it will have a maximum value equal to the standard deviation of my test when reliability is 0. All right, so that's all that I have for you today. In a subsequent, I think my next video, I'm going to talk about the different sources of error that we're concerned about in classical test theory.